Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is steel silo design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will be partially modeling the structure that you see over here on the right-hand side, as well as loading and running a full analysis within our base FEA program, RFEM 6. After the analysis, we'll take it a step further to perform the surface design utilizing the stress strain analysis add-on. So this is code independent and does provide a stress design ratio for all the surfaces that you see over on the right. We'll then move on to the AISC member design at the base of the structure, utilizing the steel design add-on. And finally, we'll talk about buckling considerations, utilizing our third add-on, stability analysis. So we'll go ahead and begin in our main FEA program, RFEM 6. So when we do launch a new file, we'll get the dialog box that we see here called the base data. And under the add-ons, these are the various add-ons that we can go ahead and turn on or off. But for the first part of this example, we'll go ahead and leave all of these add-ons turned off and get into that a little bit later on. So we'll only be utilizing the base program RFEM 6. Now, I will be generating the load combinations automatically according to the AISCE 7. You do see here many other international standards available. And we have implemented the 2022 for our load combinations. So we'll go ahead and implement that latest version there, again, for today's load combinations. So once this information is defined, you'll be brought into the main program here. And I've taken the liberty for the sake of time to define some various materials such as stainless steel, A240, grade 304, we have A53, A36, and these all just come from our material library within RFEM itself. Also some various cross sections such as some pipe shapes, MC shapes, directly from the AISC database, and then a couple of thicknesses that have already been defined, and these will come into play when we draw our surface elements. So to begin, I'm going to modify the location of this drawing grid, and I can do so by right-clicking at the bottom of the page here under Grid to edit, and to simply modify the origin coordinates to 61 feet in height. So when I click OK, we'll notice that my drawing grid is now located at this elevation. I'll start off by drawing a new circular line element. So I go ahead and select a new line, but I change the line type here to circle, where I can simply snap to that origin point. And then I can either snap to my drawing grid here, or I could directly type in the radius of 1.5 feet. I hit enter on my keyboard, and we have that initial line element generated. I'm going to modify my grid elevation once again by editing it here, and we'll go ahead and set the elevation at 59.25 feet, and we hit enter. So now that grid is just sitting slightly below that line element that we just created with that circle. I will create a new line. This time the line type will stay as a single line, where I snap to that circle point, and then I'm going to also snap to my second point down here on the drawing grid at 7059.25. I right-click to exit this dialog box, and we're going to go ahead and create a couple nodes. So we can do so right up here in our quick tools up at the top to generate a new node. Now I could either snap to a point again on my drawing grid, or I could input in the coordinates directly at 7.17, 0, and 59.17. I hit enter on my keyboard, and we see that first node generated here off to the right. I'll go ahead and create a second node at 7.25, 0 and 59 feet in elevation. I hit enter and we go ahead and right click out of this dialog box. So this is going to form the curvature of our roof surfaces here for our silo. But we need to connect these nodes with another line element, but this time the line type will be of the type arc. When we have this line type selected, we just simply choose these 3 nodes in order. We right click and now that line is complete. So I'm going to take both the straight line and the arc line and select it with my selection box shown here graphically. And we want to take advantage of our copy rotate tool in the program. So I'm going to create 2 copies here at 180 degrees, and we'll go ahead and rotate about the center origin point 0, 0, 0. But under the numbering and options, we can take this a step further by activating what we call step links. This brings up a new tab here in this dialog box where I can actually generate my surfaces between my copied lines. And when we do this, we can create a new template. And when we go into the new template options, this is just to simply assign a thickness and a material to those surfaces that will be generated. So utilizing the thickness that I've already defined in this model at 0.172 inches within my dropdown, and we'll go ahead and assign it the stainless steel material as well. So when I click OK, I change the link type to arc. I click OK once again, and now we see those surface generated for our roof structure. So now that those have been generated, we have our opening up here at the top. So I'm going to hold down my control key to select both of these line elements. And if we right click under these menu options, we have the ability to extrude the line into a surface. So this is certainly just a time-saving option rather than manually creating this surface, that we can take the existing line and we can extrude it 1 foot in the vertical positive Z direction. So this is based on those global axes here. Once again, we want to assign a thickness and a material to this newly generated surface. So we could certainly create a new thickness here. We could open up our material library to assign a new material, but these have already been defined in our model at that 0.172 inches and our stainless steel. So we click apply and now we see that surface generated here. So this is fairly straightforward for the opening up at the top here, but what if we would like to add in an additional opening to this more complex curved quadrangle surface here? Well, we certainly have opening options up here in our quick tools, but the problem with these openings is that they must be applied to surfaces which are all in one plane. And we certainly don't have that with the curvature of our roof here with this individual surface. So how can we add an opening to it? Well, I'm going to go ahead and move this to a plan view here graphically. So now we're just looking down at the top of these surface elements, and I'm going to, again, create a new line element with the line type set to circle. And then we would snap to our drawing grid where we would like to place this opening. And I'll go ahead and create my second click here to define the radius of that circle. So this is nothing more than a line element that's lying at the same plane as my drawing grid. What we do now is to right click on this line and yet again extrude the line into a surface. So this time we'll keep the height at 2 feet in the positive Z direction. We assign the thickness, we assign the material, and we click apply. So now we have this surface passing up through this curved quadrangle surface. Holding down my control key, I want to select both of these elements that are now intersecting. And we right click, and under the right click options, we have the ability to create an intersection between these surfaces. But new within RFEM 6, we can automatically create that opening as well where the intersection takes place. So we select that option and we automatically see the opening generated here within our curved surface. The program also broke apart this vertical surface into 2 various parts. So if we'd like to delete everything below the curved quadrangle, we can go ahead and turn this to wireframe view, and I can graphically use my selection options here and simply hit delete on my keyboard. So now what we're left with is the vertical surface here, the opening, and everything looks as it should be. So now that we're done with the roof surfaces, we want to go ahead and generate the silo walls. So I will hold down my control key to select both the front line and the rear line here at the base of the roof elements. And we're going to right click to extrude the line into a surface. Now, rather than extruding into the positive z-axis, we want to modify this to the negative z-axis. And we're going to give it a height of 38 feet. Once again, we assign the thickness and material. I'm going to keep this the same as all the other surfaces so far, and I hit apply. So now we start to see the silo walls begin to build here. Now, I'm going to create a couple transition points at the base of this structure and continue to increase the height of these silo walls. Therefore, I'm going to modify this extrusion depth to 3.5 feet, and I'll go ahead and just click graphically these bottom two lines. I hit apply, and I'm going to create one more transition point at 1.5 feet, and again, I just simply click on these bottom lines, I hit apply, and now our silo walls are complete. So these transitions will make a little bit more sense as we continue to model. So we're now done with the majority of the silo structure itself, other than the hopper here. So we want to create a new node. So we go up here to draw a new node, and I can directly input in the coordinate points of 1.5, 0, and 5.5. I hit enter on my keyboard. And what we should see is a node generated down here at the bottom. Now I right click to exit. And we want to draw in a new straight line element, similar to what we've seen before with just a single line. And I'm going to snap to the second point here on my silo walls down to this newly generated node. And I right click to exit a couple times. I'm going to highlight this single straight line element, and I'll take advantage again of the copy rotate tool. So the program remembers I previously created two copies, 180 degrees. We're still going to take advantage of the step links here. Now, if I wanted my hopper to have an increased thickness or for whatever reason a different material, again, we could go ahead and set that information here. But I'm going to use the same information that I've already defined. So then when we copy and rotate those lines, we'll have those surfaces automatically generated here. All right, so let us talk about the ring beam. So we know ring beams, and in our case today, will be used to transition from these 1D steel members supporting the silo structure into the 2D surfaces here. But ring beams also act as wind girders for additional lateral stiffness, so it all just depends on the silo structure that we have. I'm going to create a user-defined visibility here by first selecting this line element in the center, and then I'm going to hold down my control key to select this additional line element at the bottom. I'm going to create a visibility by the selected objects, and I'll highlight these two top line elements. When I right-click, under the options here, we have the ability for manipulation and several tools available to us, including parallel lines. So this might be something that you see similar in AutoCAD, where we can simply input in the offset distance, such as 6 inches or 0.5 feet. And then we offset it based on the line's local axes. So we can see here currently it's set to -y. So we're going to offset that 6 inches from the existing line's y axes in the negative direction. I hit apply. I'm going to do the same thing at the base line here. I hit apply. And then I'd like to create one more offset in the opposite direction here at the base of these wall elements. So I just simply modified this offset direction to +y instead, and then graphically click on those lines. Hit apply. I can right click to exit out. And now we have the existing boundary lines, which will be used for those ring beam surfaces. I want to connect these nodes though with a new line element. So we go back to the general single line. I will click on the left node, the right node. I right click once to exit. I'll do the same thing on the right hand side. And then I'll create a single continuous line at the lower left and also at the lower right. So now that these boundary lines are created, we need to actually define the surfaces here that will make up that ring beam. So we can create a new surface type up here in my drop down, but we'll choose the option select boundary lines. Because those boundary lines already exist, then we can just simply put in the thickness, but this time for my ring beam, I'm going to increase the thickness to 0.5 inches. Again, that's already defined here within my model, but we could create a new thickness directly within this dialog box as well. The material, perhaps we could modify this to A36, again, available here in my dropdown. I click OK, and then what I need to do next is to select the boundary lines. So I'll select the 4 boundary lines to create the first half of that ring beam, and then we'll do the exact same workflow here for the back side of that ring beam. Same concept down here for our lower ring beam, but this time the boundary lines will be a little bit larger. And then we'll go ahead and do the same thing at the rear of the structure. So once we close those boundary lines, those surfaces are now generated and we can right click to exit. So what we'd like to do now is to generate the members here that are supporting the structure down to the foundation. And we would normally do so by drawing a new single member. And we would set the member type here under the second tab. We would go ahead and define the cross section. We would define the material. But for the sake of time, I went ahead and have done this workflow in an already saved model. So we'll go ahead and jump to this already saved model where all of these members have already been defined here. So let us just take a quick review of what exactly the member types are, as well as the cross sections. Well, under our navigator options, and specifically the second tab for our display properties, I can scroll all the way to the bottom to take a look at the colors shown here graphically, and I could change these based on the member cross section. So what this is showing me now are the various cross sections that I have defined. You'll notice for these main columns here, these have been defined as a pipe extra strong, 10-inch diameter, A53 grade B material. Now we have some smaller pipe elements here for our lateral stability as well as their horizontal members. These are just standard pipes, 5 inches in diameter. And finally up here at the top, spanning between the 2 ring beams, I have some MC shapes, again, directly from the AISC database within the program. They're just providing additional stiffness here between the transition of my silo walls to my hopper. So that covers the basic cross sections that are used, but I'm going to modify the view now to the member type. So now we have these various colors here based on the member type. And what I mean by this is if I double click on one of those main columns, you'll notice that the member type is set to beam. So beam is just anything that's a standard column or beam. By default, the member is considered fully fixed at either end unless we add in a hinge option here to release the moment, for example. But we'll leave everything fully fixed here. We also have these purple members, and the purple diagonal members are set to the member type tension only. This means that the program can only, or that these members can only take tension forces. The minute that they have a compression force, they'll be taken out of the calculation entirely. But because RFEM is a nonlinear analysis program, in a subsequent iteration, if tension forces are reintroduced, then we can also reactivate that member. And finally, we have this green member in the back, which you'll notice is a different color than the rest of our columns. So what's interesting about this member is we actually just released it in RFEM 6, and it's of the member type surface model. Now, at first glance within this dialog box, it really doesn't seem too much different than a standard beam element. You'll notice under the section, we still define this as the extra strong pipe, A53 grade B material. But this will definitely come into play later on when we take a look at the FE mesh as well as our results. So I'll explain this member type in more detail as we go on, but just notice now it is a slightly different than the rest of our column elements. I also have placed in here some nodal supports at the base of our columns. These are just applied here directly within our quick tools. Okay, so now that we have discussed the member modeling and have done a quick overview, let us talk about the surfaces and the importance of local axes orientation. So in our navigator, we're going to jump to this third tab here. And this allows me to turn on and off various elements within the model. So I'll begin by turning on my surfaces and only the stainless steel surfaces. So everything else is hidden in the background. I'm going to right click to turn on the local axes of these surfaces. So if you notice, these local axes are right now oriented in various directions. They're certainly not all going in the same direction. So this is a problem and incredibly important when we're doing any FEA of surfaces that we want to ensure that the local axes are oriented in the same direction for a couple different reasons. The first is for loading considerations. Much of the loading that will apply to this structure today is based on the local axes. So for example, if we have the z-axis facing inward for some of these surfaces, but facing outward for others, that's going to affect our ease of applying loads. The second issue is result interpretation. So information, once we run the analysis, such as surface internal forces, stresses, these are all based on local axes. And again, if we have adjacent surfaces that have varying axes directions, then our results are also not going to make much sense. So let us begin with the local z-axes. So currently most of these surfaces here, with the exception of our hopper and with the exception of this surface in the lower left here, are all facing outward. So we can modify these by selecting them and holding down our control key. And then we can right click to simply reverse the local axis system. So now you'll notice that the z-axis is facing out for all of our surfaces. So this is certainly a good start. But the next problem is, if we take a look at these larger wall surfaces, we have the y-axis facing upward here on the left and facing downward here on the right. And the same goes for some of these other various surfaces. So I'm actually going to highlight all of my vertical surfaces, including the hopper, as well as these surfaces up here at the top by holding down my control key. Now I can easily double click on these surfaces to jump into the Edit Surface dialog box, and we want to turn on the Specific Axes option. This brings up a new tab at the top of this dialog box called Input Axes, and under this drop down we want to select the option Axes Parallel to Lines. This allows me to tell the program to orient all selected surfaces here and their y-axes parallel to a line that I can just arbitrarily choose within the model. So I can graphically select any line back here within the model, and I can easily just choose, we'll go ahead and turn on our visibility of our lines, choose this line element here, number 49, for example. Notice when I hover over it, the red arrow is showing me the line orientation from bottom to top, because that will affect how we orient our local y-axes. So I select this line number 49, I click OK through these dialog boxes, and now you'll notice that all of my local y-axes are now oriented in the vertical direction. So this takes care of those vertical surfaces, but we need to address the roof surfaces here as well. So I will select the smaller surfaces that define that curvature, as well as my two quadrangle surfaces. I'm going to create a visibility by the selected objects, and you'll notice the first problem we have is all the z-axes are facing inward. So we select all of these elements here, we can right click, and under our surface option, we have the ability here to reverse the local axis system. So now all these z-axes are pointing outward, similar to the rest of the surfaces within the model. The next problem though is the y-axes. So for these, I'm actually going to select all of them, double click, and once again under the specific axes and input axes options, I'm going to use my drop down to choose the option axes directed to point. So I can tell the program, instead of setting these parallel to a line, I'm going to set the local axes, the local y-axes, directed to a point that is passing up through the center of my silo structure. So I can graphically choose this axis that I would like to point these local y-axes to my surfaces. Sorry, I can directly choose the coordinate points is what I mean. Or I can just simply type in some type of arbitrary vector. So 0, 0, 0 and 0, 0, 1 is enough to orient those y-axes towards the center of the structure. This way, when I click OK, you'll notice now that each y-axis is pointing right here towards that center point. Okay, so now that we have modified all of the local axes systems, we can go ahead and cancel our visibility mode. And the next thing we'd like to talk about before running an analysis is our FE mesh. So if we go to calculate mesh settings, we will see here our target length for finite element. So this is our global mesh settings, and the default is set to 1 foot. If I click OK and apply, the program will go ahead and generate this mesh for me. Now, under my navigator display options, it could be that your mesh is turned off. So all we need to do here is to turn that back on. I'll turn this to wireframe view, and you can see that the program has automatically meshed everything for us based on that 1 foot setting, including tying all the members into the mesh. Everything again is done automatically. But the problem is that this mesh is a little bit too coarse. For example, if we look at these smaller vertical surfaces here at the openings, there certainly are not enough FE mesh along the height, so we'd probably want to refine that further. One option is just to go back to the mesh settings here. We could certainly set this at a smaller value of 0.5 feet. We can hit OK and apply. And now you'll notice that we have additional FE mesh elements. Looks a little bit more refined everywhere in the structure. Now, for my example today, I am going to keep this at the more coarse mesh size of 1.0 foot, and that's just simply to get a quicker calculation. But for your own projects, you certainly would want to refine that further. Now, remember back to this special member type here, surface model, and that it's a different member type than the rest of our columns. Well, we'll actually be able to see that now if I scroll up to my navigator display options to the top under the members tree, we have here a checkbox for surface model. So when I turn this on, notice that we have an FE mesh generated for this column element. So what's happening here is that the program has created the 1D member element, as we see with the rest of the columns, that we can move forward with the AISC design and the steel design add-on a little bit later on, but it's also creating a secondary element here for the surface. And this surface will allow me to perform a more in-depth stress analysis and design, for example. You'll also notice that the FE mesh is much more refined than the rest of the structure. So if I go ahead and highlight this surface and take a look at the dialog box here, the mesh refinement is activated for this specific surface. And under the mesh refinement, we can see here that the program has automatically detected that we're going to have to set a smaller mesh size of 0.1 feet, but I can always adjust that if I'd like. And then it will transition into the rest of the surface elements, which have a global mesh setting of 1 foot. So you can certainly apply mesh refinements about nodes, about lines, about specific surfaces, as we see here. You're not confined to only the global mesh settings. But this is an important feature, again, of this surface model member type that we'll take a look at our results once we are able to run that analysis. But just keep that in mind. That's what's going on underneath the hood. Okay, so we're now ready to move on to loading. So I'll go ahead and deactivate the mesh here. And if we go into our load cases and combinations dialog box, remember under the base data, we are generating our load combinations automatically to the AISC E7, the 2022 standard. The combination wizard, when this is checked on, the program will automatically generate our load combinations referring to the standard. Alternatively, I can just uncheck this if I'd like to manually create my load combinations instead. Under our load cases, the program creates our first default load case called self-weight. If we'd like, we could rename this one to dead load. We would want to assign the action category here to dead load. This is specific to the AISC 7, so the program knows which load factors to apply to which load cases. Now for my dead load case, I'm actually not going to apply any additional loads to our structure. We'll go ahead and leave that as self-weight only. But I will create a second load case, and we're going to call this one pressure horizontal. And this is for our fill load that's going to go inside the silo that's going to create this outward pressure. Now the action category, if this was a fluid load, we could certainly set this to F. For today, I'm going to set this to live load. So now that I've generated this load case, I click OK, and I'm back here within the program, but notice load case 2 is selected within my drop-down box. Now with this fill load, I am going to assume that I'm not going to fill it up to the full height of the silo walls, up to the very top here, but rather we know this fill will be at a maximum a couple feet below the top of the surface. So I can't simply apply a simple surface load because that will apply it along the full height. So instead, we want to utilize what we call a new free rectangular load. And this just gives us a lot more flexibility with our structure loading. Within this dialog box, the first thing we want to do is to specify the load projection, and this will be in the XZ plane. We also want to apply the load based on the surface's local Z axes. So again, this is why we oriented all of those local axes in the same direction, because this will make our lives much easier when it comes to loading. The load distribution is going to be linear in the Z direction. So what I mean by this is at the bottom of my silo, where most of that fill is sitting, we want to have a higher pressure of 2.5 kips per square foot. But at the top of the silo walls, we want to linearly transition to a magnitude of 0. So now that we have these load magnitudes defined, we need to actually tell the program where to apply the loads along the structure height. And I'm going to do so by graphically selecting 2 points here. Now, before I select my 2 points, I'm going to turn back on my drawing grid, and notice it's already arranged in the vertical direction here. But I'm going to snap that drawing grid origin right up here to the center of the structure. So we'll choose this point at the base of the silo wall. So if I rotate this around, just notice that that drawing grid is snapped right up to the front face. And I'm going to modify my view here in the Y direction. So now when I'm applying this pressure fill here, I can choose a point at the base of my wall. And my second point will be to a height of 56.5 feet in elevation. Notice I'm not snapping to a point at the top of my wall element because I know my fill will not be that high. Then I'm going to graphically select the surfaces, the vertical wall surfaces here that I would like to apply this outward pressure. The surface numbers are generated here. I click OK through these dialog boxes, and now we can see that outward pressure applied to the structure. Now we want to do the same thing down here for our hopper. However, for the hopper, we do want to apply the pressure from the bottom all the way to the top. So instead of using a free rectangular load, it's much easier just to choose a new surface load for this condition. The load type will be set to force. The load distribution will be yet again linear in the Z direction, and we want to apply this based on the surface's local Z axes. The load magnitude here will be set to 0 kips per square foot at the bottom of our hopper, but up at the top, we want to increase that pressure back to 2.5 kips per square foot. Now the program is asking me to select some nodes here to define how this magnitude should vary along the surface height. So I'll simply select the bottom node here for the 0 pressure magnitude, and then my second node point will be at the top of the hopper where I'd like it to increase it to 2.5 kips per square foot. I will graphically select here my 2 surfaces, number 8 and number 12. I click OK, and now we have this outward pressure. If you find that the display of your surfaces is a little bit too big, we can always right-click here under Display Properties, and this will bring us directly to this specific loading under the Display Property controls, where I can modify the size here of 1 KSF to something much smaller. I click OK, and now we can right-click to use our slider options here to increase or decrease the size of this loading. But more or less, we have this outward pressure here at the hopper as well. So we want to move into our next load case to represent some type of friction load for our film. We're going to go back to our load cases and combinations, but this time I want to take load case 2 and I'm going to make a direct copy of it. So I now have load case 3, and we'll rename this one to pressure vertical. And I'm going to click OK to come back into the model. But what you'll notice is that now I have load case 3 available to me. And by copying the existing load case 2, I've also copied those loads. So this allows me to double click on this free load. I can modify the load direction. Instead of based on the local Z axes, I'll modify it to the local Y axes. I'm going to also change the magnitude here to negative 0.1 kips per square foot. I click OK, and now that load is automatically modified here. So I don't need to redefine the free rectangular load. I can do the same thing down here for my hopper surfaces. I'm just going to modify the load direction based on the local Y axes. I'm going to modify my load magnitude here to negative 0.1. I click OK, and now that load was also quickly modified. So there's certainly an advantage here of making a copy of that existing load case to not have to redefine those free rectangular loads and surface loads again. Now, for our final load case, we will just generate a new load case rather than making a copy. And the wind load, this will be of the type wind with the load case name set as so. The action category will, of course, be set to wind load. So now that I have this fourth load case, what I'd like to do is refer here directly to the AISC 7 2022. And in particular, I'm looking at figure 30.10-1. So if we are designing our silo according to the components and cladding method for our wind loads, you'll notice here that we have a rather complex scenario where these wind loads will actually vary as we move around the circumference of the structure. Now, how we vary the magnitudes of the wind loads all depend on this table given here with the external pressure coefficients that are further dependent on the height to diameter ratio of our structure. So how do we apply such a complex loading as we see here in figure 30.10-1 and easily do this in RFEM? So we'll go back to the program here, ensuring that we're under load case 4 for wind load. And I'm going to, again, apply a new free rectangular load. The load projection will be in the XZ plane again, and the load direction here will also be according to the local Z axis. So this is previously similar to what we saw with the load film. The load distribution, though, will be varying along the perimeter. So notice how our picture updates over here on the right-hand side. Now we do need to give a starting load magnitude, and we're going to set this to negative 0.02 kips per square foot for our wind load. But under our second tab, this is how we can tell the program to vary this wind load as we move around the circumference of the structure. The first thing to define is that center axis point. We previously saw something similar to this before with the local axis orientation. I can either graphically select these points here within the model, or I can just more or less select a couple points that define that vector right up through the center of the structure at 0, 0, 0 and 0, 0, 1. This table down here is where I define in degrees how I'm going to vary that 20 pounds per square foot with a factor, again, as we move around the structure. So what I've done in this Excel file is to actually export out that table. And then the table was initially empty. So under this column B, I've now put in increments of 15 degrees, starting at 0 all the way up to 360 degrees. I referenced figure 30.10-1 for my specific structure to determine what those external pressure coefficients should be. And I input them in here in column C. So now back within RFEM, I have the ability to directly import in that Excel file with this button shown here. So the program will refer back to the open Excel file, and back in RFEM, we'll see all these values automatically imported, and the program will then calculate the load in this third column, again, varying as we move around the circumference. So now that this information has been input back under the main tab, what we need to do is to assign the corner points of how this load should be applied to the structure. So I'll select my 2 points here, and I want to turn back on that drawing grid, and it should still be snapped here to the front face. So we'll modify our view based on the y-axis. Now this wind load will be applied from the base of my hopper all the way up to the very top here of my silo walls. So I've defined those corner points, and lastly, I need to define the vertical surfaces here that I would like to apply this wind load. So I can just use my selection box to select all of the surfaces shown here within my dialog box. I click OK, and now we see that outward pressure. I can take a look at the view here in the global Z direction. And again, this should reflect what we see within the AISC E7 with my wind load flowing from left to right here based on the global X axes. Now, realistically, we'd probably want to add additional wind load to our roof surfaces, to our members, but I think more or less you understand the concept now of loading. So we will go back to our load cases and combinations. Now that these load cases have been defined, the program will automatically create what we call design situations. And these design situations just simply group together all of our load combinations. So we have our first design situation, which is our factor load combinations. And we have our second ASD design situation, which will be our unfactored load combinations. Now, for our example today, I'm not so interested in checking deflections and things like that for my silo. So I'm really just going to keep here my LRFD design situation and deactivate the ASD. The design situations will come into play a little bit later on within those design add-ons. And lastly, we have our load combinations here individually listed out based on the load cases that we've defined with the relevant load factors directly from the AISC E7. And again, these all belong to this single design situation as noted under this previous tab. So we can view these various load combinations here with all of the loads and applicable load factors applied graphically. And we can scroll through those here to see them again applied to the structure. So we'll now go to calculate all. And remember, RFEM is responsible for the analysis portion only. So what we're going to do now is to go ahead and solve each individual load case, but we're also solving for all of our load combinations listed here. And these load combinations are being solved according to a nonlinear second order analysis, considering both big P delta and little p delta. And also notice that the program is taking advantage of the multi-core processor in your computer to solve these load combinations at once. But now that the calculation has finished, we are presented with a fourth tab here in our navigator for our results. And we're currently looking at the deformation of the structure under any one of these specific load combinations. If I'd like, I can modify my deformation of my members here to be colored cross sections down at the bottom, so that's a little bit more visible to you. So taking a look at the global deformations, we would just want to ensure that we see results here that match up with what we would expect under the applied loads. And once we have taken just a brief overview of that, another way to check our load input is a nice feature in the results called distribution of loads. So I can back up a step to go to my wind load case. So this is the load case with only wind defined. And I'm going to set the display here based on the global x-axis. Notice that I can now see how this wind load was distributed to my surface, again referring back to the AISC 7, where we should see varying wind loads as we move around the circumference of the structure. At the front, we're going to see that 20 pounds per square foot, but as we move around, we'll see the varying magnitudes, including a pressure or a suction in the rear of the structure. Same concept for that fill load, that horizontal fill load. If we'd want to modify this based on the local z-axis, we can take a look at here, and we'll see at the base of our walls, we should be seeing a value pretty close to 2.5 kips per square foot, but at the base of our hopper and at the top of our silo walls, we transition linearly to a magnitude of 0 kips per square foot. So again, just a nice feature to ensure that we've applied our loads accurately here. Now, in addition to checking the distribution of loads, we're likely interested in our members. And within our members, we can turn on this option here within our results to view the axial forces. We can view our shear forces, as well as bending moments in the strong axis, weak axis direction. For all members visible here, perhaps we'd like to change to these different load combinations and view our results here. This information is also available in table format under the static analysis. We can go to results by members. We see here internal forces where we could export out to Microsoft Excel. Now jumping to the results of our surfaces. So we'll go ahead and turn on our surface display here, and we could view internal forces, but I'm going to turn on my stresses, and in particular my von Mises stresses. So we currently see those von Mises stresses shown to us graphically here. But if you remember, we have this special member type that created that FEA underneath the hood in addition to the 1D member element. Well, back under my navigator display options, if I turn back on that 2D surface and I take a look at here the visibility by the selected objects, notice that we're getting stresses for that one-dimensional element because again, that 2D surface was also generated for that more in-depth stress design. So this might be very interesting for us, not only to view the internal forces in the members, but what are the stresses where it's framing into this ring beam. So keep that in mind that that's what's happening again underneath the hood. We'll go ahead and exit out of this visibility mode back to the general display here of our silo surfaces. You'll notice that currently I'm looking at the von Mises stresses, and the highest stress under this particular load combination is 229 KSI. I think we're all in agreement that this is much too high, that likely the steel material will yield at a value much lower than this. And if we take a look graphically here, we see that this is really a result of a singularity, essentially where we have all these high forces framing into this one single nodal point, when in reality, we're gonna have better load distribution. But here is a trick within the results interpretation. When you are looking at stress analysis and design, for 2D surfaces or 3D solids, it's highly recommended under the calculate result smoothing to change here the default option. So currently the program is using this smoothing algorithm to tie in all these values so that we have a nice view of the ISO lines and contour lines here back within the model. But it would be better, again, if we're doing an in-depth stress analysis and design, to change this to constant on mesh elements. So the picture won't look as nice, but your values are going to be a bit more accurate. Notice that for every FE mesh element now, it will have its own value rather than trying to tie it together all within the single surface. So notice that my values were previously set at 229 KSI for this particular load combination. When I change this to constant on mesh elements, we drop to 21 KSI. I mean, this is a very significant difference. So again, it's highly recommended to make that modification when we are doing this stress design. Okay, so now that we have taken a look at our analysis results, let us move on to the design with those specific add-ons. I am going to go back to my navigator here, and I'll right click under the member name to launch the base data. And if you remember at the beginning of the example, I showed you all of these various add-ons. Well, now we'll make the clear distinction that we're going to activate them. So everything you've seen up until this point has only been in the base program RFEM 6. So we're going to launch the stress strain analysis, the steel design, as well as structure stability. And I'll go through each one of these in that order to explain how we can perform the design on the structure. So taking a look first at the stress strain analysis, I am going to highlight my entire structure, and I can double click on my surfaces here to go into the edit surfaces dialog box. You'll notice now that we've turned on that stress strain analysis add-on, we have an additional tab here. And this is actually pretty straightforward. We have a configuration, and the program already has a default setting here that we can take a look at. So the program automatically suggests that we'd like to design these surfaces based on the normal stresses, which are turned on here. We have shear stress as well as von Mises stresses. And we can turn on the other various stresses if we're interested in designing those as well. But we get a nice formula here along with the variables and variable definitions. Now, in this second column, this is the limiting stress type. What this means is that the program needs that limit stress defined. So typically we're just going to refer directly to the material itself. For example, a 36 material would have a limiting value of 36 KSI for something like von Mises. And with these drop-down options, we can refer directly to the material, or we can set our own user-defined value if we'd like. Now, keep in mind, this add-on is completely code independent. Rather, we're just doing a general stress design specific to the material's capacity. So once we have adjusted these configurations and which stresses we're interested in, that's really it. We can click OK, and what we'll see down here in our table settings is a new option for the stress strain analysis add-on. Under design situations, remember I said that the design situations will come into play a little bit later on with the add-ons. Well, here we have our factored design situation, which includes all of those factored load combinations, and this is automatically checked on here. We're not interested in our unfactored load combinations, so we deactivated that. The objects to analyze, we can do a general stress design of the members as well, but we're not interested in that today. We're only interested in doing the stress design of all the surfaces. Now, before I run the calculation, I want to make one more modification here in the global add-on settings. So this is somewhat independent of the base program RFEM 6, but more specific to the stress strain analysis add-on. And very similar to how we change the smoothing settings in RFEM 6, we need to do the exact same thing in this add-on. Otherwise, the program is going to refer to those extremely high stresses where it's trying to use that smoothing algorithm to tie the stresses together. So instead, we change this to constant on mesh elements. I click OK, and now I am going to run the calculation directly within this table. So unfortunately, when we activated the add-ons, it did clear our results, and the program just made a quick note of that, and no problem. All we need to do here is to run back through these load combinations to determine the demand stresses. So what are the stresses on each one of these surfaces based on the applied loads? So once that these have been determined here, as you can see, some of these are wrapping up, it brings in those stresses to the stress strain analysis add-on, compares it to the limiting stresses of the material itself, and ultimately what we're presented with is a stress design ratio. So we can view these stresses here on the surface under the stress strain analysis, and sure enough, we have our existing stresses, we have our limiting stresses based on the material, and then we have that general stress design ratio. So as I click through this various table, notice that that red arrow is pointing me directly to where that controlling stress is on the surface. And if I like, I can also take a look at the result details. So these design check details here are just going to list out, again, the formula for the stresses, all of the stresses from the analysis, the limiting stresses, and ultimately how we calculate this stress design ratio. So trying to be, again, as transparent as possible where that information is coming from. So that's really it for the general surface design. So you can see how this is a little bit more efficient rather than having to manually export out our stresses to something like Microsoft Excel to do that stress design by hand. So we'll move on to the steel design quickly. Now, of course, there's not enough time today to go into detail for this, but I do have additional webinars that are devoted to each one of these add-ons that go through this workflow in much more detail. But for today, we're only interested in designing quickly these 4 column members. And if I double click on these 4 columns, we have all of these additional tabs available, again, because we activated that steel design add-on. So the one thing we need to do before running our design according to the AISC is to define our unbraced lengths. And we do this under the design types effective lengths. I create a new definition type here. Now for these circular pipe members, I'm not so interested in torsional buckling failure modes, lateral torsional buckling. Rather, I'd rather like to just check flexural buckling in the strong and weak axis direction. And under this second tab, the program is automatically placed in these intermediate supports internally to help calculate the unbraced lengths for flexural buckling. But remember that we also have these smaller pipe segments here framing into both the strong and the weak axis for these columns. So we can add in that intermediate node, go ahead and manually place in that intermediate restraint. And now the unbraced length will span between these intermediate nodes at 8 feet or 1/2 the height of the full column. So now that this information is defined here, what we can do is to drop down to the steel design add-on. Very similar workflow here that we saw with our surfaces. We have our LRFD design situation and we set this to our LRFD strength limit state. Under the objects to design, I'm not going to design all members. Rather, I'm just going to go ahead and graphically select here my 4 vertical columns, and I can run my calculation. Now, I already have my internal forces. It brings it into this add-on. It applies the AISC equations to ultimately give me my design ratios here for each one of these members. So again, notice within this table, everything is synced up graphically, and we have all of the various checks here directly from the AISC. For these various checks, we can take a look at our design check details, and we see here our code equations given to us. I can use my mouse wheel to scroll in to make this larger. We see the code equations line by line, the variables, the code references, ultimately how we're determining this design ratio. So again, just trying to not be a black box software, but to give you as much information so you can determine if you agree with how the program has ultimately calculated this design ratio. And this is true for all of the various checks within this member. We can also scroll through to the various load combinations and so on. So point being that we can design both the members and the surfaces within the same model in RFEM 6 with those available add-ons. The final topic to discuss in the last few minutes is buckling. So when we are performing a general static analysis, buckling is not necessarily considered. Now, if you're running a second order or a large deformation analysis, the program will give you an instability if you exceed the critical buckling load of either a surface or a member. But it's just a general instability without much more information. So how can we take structures such as this to evaluate buckling considerations? Well, if you remember, I activated the structure stability add-on. So we'll go back to our load cases and combinations, and let's take a look at load combination number 3, for example. Well, for any of the load cases or load combinations, we have this additional setting to activate the structure stability add-on. And I take a look at my default settings here. This allows me to run this eigenvalue analysis and determine the number of eigenvalues that I have set. So you can see the default is 4 for this definition type. We have a second definition type set to 10, or I could just manually type in however many eigenvalues, 50, 100, however many I would like to calculate. Now for our example, we want to use this default 10 eigenvalues. So I go ahead and select it from my dropdown, and I'll immediately click calculate to just calculate load combination number 3 here. So while this is running, I just want to quickly explain what is the benefit of this add-on and kind of what's going on with the calculation right now. So we have run the static analysis load combination shown here in line 1, but line 2 is running that eigenvalue analysis. It's going to import in all of the axial loads on the surfaces as well as the members. So you certainly want to choose a load combination that has the highest gravity loads, for example. And we're going to determine the 10 failure buckling modes of the structure along with the critical load factors. So this will just help us evaluate where we may potentially have issues with buckling with the structure. So now that this is complete for load combination number 3, we can see here not only do we have the static analysis, but we have the stability analysis, and we have our 10 different eigenmodes that we solve for, as well as more or less this mode shape shown graphically on a scale of 0 to 1.0. So no magnitudes because it is an eigenvalue analysis. But we see here in the table, here is our first failure mode. So essentially it looks more or less like the racking of the entire structure with a critical load factor of 2.2. This just means that the program can handle 2.2 times the loads from load combination number 3 before we would see a failure mode as this one. If we take a look at the second failure mode, again, more or less just racking of the structure in the other direction. But then we start to see failure modes here, buckling of our column elements. And if we continue to scroll down through these, eventually we get to mode shape number 9 here. And this is where we start to see failure modes or buckling of the shell elements themselves. And I can decrease the factor here, so this is not so overwhelming, but we kind of see the buckling here of, again, the silo wall. But notice the critical load factor is 41.54. So this is extremely high. We're certainly going to see failure of our columns, for example, before we might see failure from buckling of the shell elements. If we have critical load factors that are down around 1.0, that's certainly a problem that we would probably want to increase the member sizes, increase the thickness of the shell elements. Anything below 1.0 means that the structure cannot even handle 100% of the loads from load combination number 3. So that's a major problem. But some of these higher critical load factors, really probably not so much a concern. But 2.2, 2.42, that's certainly lower and closer to that 1.0. We also have the ability in the program with the imperfection options that we can export out this buckling mode shape to deform the FE mesh before we continue on with the full static analysis. So imperfection options are available in RFEM 6, and we obviously don't have time to show you that today. But if you're interested in more about how we can deform the mesh, which we would see higher stresses then after the analysis at these locations, then certainly let us know and we'll be happy to send you more information. But essentially, more or less buckling considerations, you would want to take advantage of the structure stability add-on as we've just seen. Okay, we will go back to the PowerPoint here to conclude our presentation today. So this presentation is recorded and will be placed on the same web page that you use to register, usually within the next day. You can also download the silo structure model and open it up within the free 90-day trial version of RFEM. RFEM 6 does include all of these add-ons that you've seen. It's full capability for the trial for a full 90 days. If you have any questions about today's presentation or anything else, feel free to contact us at our Philadelphia office. Our phone number is 267-702-2815, and our email is info-us@deluwald.com. So we will have many more upcoming webinars. We certainly have some exciting new features coming up, new releases that will hold webinars on. You can register at duluwald.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so you can continue to sign up directly through there. PDH certificates will automatically be emailed to all participants who are here for the full presentation. That is a requirement of the states that we are pre-approved providers, that you are here for the full duration of the presentation in order to receive that PDH. It's not sent out automatically after the presentation. Please give that just about a day or so before you'll see that email come through with your PDH. Now, if you watched with a colleague or in a conference type setting and you yourself did not register for this webinar with your own name and your own email, you will need to request that PDH here at info-us@duluwald.com. So again, if you yourself did not register with your own name and own email address, please request that PDH to the email shown here. Let us know who you watched it with, and we'll certainly get that over to you. And with that said, I want to thank everyone for attending, and as always, we hope to see you at our next presentation. Thank you.